Okay, so welcome to Math 317. This is lecture 3. And what I want to do today is I want to review a little bit of linear algebra. I know some people, it's been a while since you've done linear algebra, so I figured it's not a bad idea to spend some time today just going over the key concepts and just also talking a little bit about why are things defined the way they are. So I know frequently in introductory math courses, you're given, here's the definition, here's how we do things, without necessarily being given the motivation as to where did this come from. And there should be a good reason behind it. Does anybody know what the factorial is, like 3 factorial or 5 factorial? 3 times 2 times 1. And 5 factorial will be 5 times 4 times 3 times 2 times 1. Does anybody know what 5 double factorial is? Has anybody seen the double factorial? Yes, it's every other one. And the reason is the factorial of the factorial doesn't seem to really arise that much in combinatorics, but the product of every other one arises very frequently. In fact, if you look at the moments of the standard normal, the odd moments are 0, and the even moments, the 2mth moment is 2m minus 1 double factorial. So when you're doing things in mathematics, you always want to think about, what am I going to be using this for? What is it good for? All right, so we started talking last time about matrix multiplication. I talked a little bit, imagine you have some vector x, y in the plane. We can write it as x times 1, 0 plus y times 0, 1. And then we define a linear transformation. And so what's really going on is I just need to know, what does the matrix do to the vectors e1 and e2? And then by linearity, I know what A does to V, because A x e1 plus A y e2 is x times A of e1 plus y times A of e2. So we just have to define what goes on for 2 vectors. And so if we look at what's going on, so if I have my coordinate axes here, if I start off with my vector e1, I can say, well, what does e1 go to under the matrix? Let's say it goes to some vector here, AC. And my matrix, my transformation is going to take a vector with 2 components as input and give me a vector with 2 components as output. We don't have to have square matrices, but let's keep things nice. And so if I want to represent that, my transformation sends E1 to AC, and it will send E2 to BD. And this is now how we get the matrix definition. And so if you look at, if we define the matrix multiplication A, B, C, D on X, Y as AX plus BY, CX plus DY, that's the same as taking the vector AC multiplying by X and the vector, that's a B, see, that should be a BD. Yeah, I didn't think I could actually erase that because it's an image, not a, okay. So I can draw this like a hard D like that. So apologies for the typo. When you see typos, of course, please feel free to speak up. Okay, so does this motivate the definition we have of matrix multiplication? What we're really doing is we're fixing what the transformation does to 2 basis vectors. And then we say we can write anything else in terms of them. And then this gives us a representation of a transformation in a given basis. If you change your basis, the transformation will look different, but it is still the same transformation. So then the next thing is, if you can do something once, why not do it multiple times? So let's say we have, B acting on A acting on V. This should be the same as some new matrix C acting on V. And we need to choose a way to define matrix multiplication so that if I act by A and then act by B, that's the same as acting by a new matrix C. Well, now that we know what's going on, I need to figure out what does it do to the, say, the unit vectors, the 1, 0 and the 0, 1. We can unwind this. And if we have, B11, B12, B21, B22, A11, A12, A21, A22, This is going to be B11, A11 plus B12, A21. Is this enough details? Everybody comfortable? Okay. And then I'll just fill in the rest, and that's going to be C11 and so on. Okay, so this is where the matrix multiplication comes from. It's a very natural definition to use. Okay, so this is one of my favorite algorithms in all of mathematics. This is the Strassen algorithm. This is not the best way to multiply matrices. Do not bother writing this down. The slides are posted. You can just look it up. The point to remark is, if I want to multiply matrices naively, and I use the standard definition, how many multiplications does it cost to multiply? So if I want to calculate A times B, how many multiplications is it? 8. So it's 8 multiplications. And how many additions? 4. But again, the additions are pretty cheap relative to the multiplications. What we're doing is we're doing 2 by 2 matrices. Normally you use lowercase letters for 2 by 2, for matrix elements. We're using uppercase because the real power of the Strassen algorithm is not just for 2 by 2 matrices, but for extremely large matrices. If you do a lot of things in the real world, you eventually discover it's really nice if your size is a power of 2. You can split things up and you can basically bootstrap and take things from small values and extrapolate, extrapolate, extrapolate. And so if I have a very large matrix, I would put into giant 2 by 2 chunks. Unfortunately, not every integer is a power of 2. In fact, almost no numbers are powers of 2, percentage-wise. So what do you do if your matrix is not a power of 2? Any thoughts? So it'd be wonderful if we had a matrix that was powers of 2. We don't. What could we do? So you can just pad the matrix, just put in a bunch of zeros. So just extend it up to be a larger matrix so that you could then use something like this. Or maybe you use this for some part of it and then you use something else for another part. But it's, if you have a choice, if you had to choose between doing something that's 1,000 or 1,000 what? What's a number that's close to 1,000 that might be a really good number to work with? 1,024. 1,024 is probably a better choice. And so just keep stuff like this in mind when you're choosing things. It's often very nice and clean if you have a power of 2. Okay, so the Strassen algorithm is defined the following 7 objects. Okay. How many of you have taken computer science enough to know P versus NP and problems like that? All right, so if you're familiar with that, there's a whole industry about how difficult are certain types of problems. And we'll get into that later in the semester. There are a lot of problems which are, we believe, very hard to do, but very easy to check and answer. Factorization is a wonderful example. We believe it's hard to factor. Why? Well, it's been a couple of 100 years and no one has been able to come up with a good algorithm to factor. That does not mean that there isn't one. It just means we don't know one. Is it easy to tell if a factorization is correct? Yeah, just multiply the 2 numbers. And it's going to be polynomial in the number of digits. So it's not going to be that bad to multiply 2 numbers. So for a lot of things, it's often very easy to check and see if something works well. The genius is coming up with these 7 choices. Once somebody has blazed the trail, all we have to do is check and see if this works. I have never actually checked. I probably should at least once in my life go through. I trust the math computer science community that they have checked this and this works. How many multiplications does it cost to get the 7 n's? So it's 7 multiplications. For additions, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I get 10 additions. And then when I come down here, I mean, subtraction, of course, is the same as an addition to me. I don't discriminate. When we come down below, I've got another 3, 4, 5, 6, 7, 8, another 8 more additions. So at the cost of an additional 14 additions, we can decrease the number of multiplications by 1. And amazingly, that's a great choice. So again, pure mathematics, this doesn't matter. Applied mathematics, this allows us to reduce the complexity of matrix multiplication. Rather than something that takes on the order of n cubed, it's now going to be roughly on the order of n to the log of 2 base 7. So we're saving 1 multiplication. So the log of 8 base 2 is 3. The log of 7 base 2 is about 2.8. And so I went to mathematics and I just plotted x cubed versus the log of x to the log of 7 base 2. And so when you look at this, you can see that the runtime is definitely much greater for x cubed. Well, you would expect it's a higher power. When you look at a plot like this, it's a little bit hard for me to see exactly what's going on. So a lot of what you always need to do, especially if you're talking to clients, is figure out what is a good way to present data so that you can understand. One very natural thing to do for something like this is to do a logarithmic transformation. And then you would get actually 2 straight lines. Another thing that I thought might be good for something like this is I plotted the ratio of the 2. And this is about x to the about 0.2. And it shows you that when we have an input of size 10 to the 7, it's going to take about 22 times as long to run with the standard naive approach as it would to use the Strassen algorithm. So that gives you a sense of how much better Strassen is. It's a factor of 22 savings for inputs of size 10 million. If your matrices are very small, it's probably not really worth it. Computers are so fast that you're not going to notice the change in time. But if you have a tremendous amount of computations that you're doing again and again and again and again, any small savings really adds up. And that's one of the real themes of this course, is to think, is this something that you're doing again and again and again? If so, what kind of savings can you do? And of course, once you have the Strassen algorithm, then the race is on as to what is the best you can do. And so if you're interested, you should do some searching online and see just how low can you get the exponent. Are there any natural thresholds where you would be very skeptical if someone said, we reduced the exponent from cubes to 2.8, the log of 7 base 2. Is there anything below which you just don't believe you can do? For an n by n matrix, we start off with n cubed multiplications. Then we got to n to the log of 2, the log of 7 base 2. Is there a number where you can say, Professor Miller, I just don't believe you can get below this? Any thoughts?
O of n.
Good. So why can't you do better than O of n? Why? Okay, but how many elements does the matrix have? N squared. So I would actually bump your order n up to order n squared. I've got n squared entries that I need to get. I find it very hard to believe that I'm not going to need at least n squared multiplications, that everything should be coming into play at least once. And so I would be very skeptical if somebody tells me that they can get an exponent less than n squared. Well, technically an exponent less than 2, a process of size n squared. Okay. Any questions on Strassen? Continuing the linear algebra review, this actually goes back to what, when I was a child, was in Algebra 2. They seem to have moved it now to pre-calculus. And since my kids are going through these classes right now, I actually have very good access to what is being done or not done in our schools. How many people remember conic sections? How many people remember that they at least did conic sections at some point in school? So essentially, if I give you a cone and I look at slicing the cone with planes in different ways, I get different shapes. The simplest is if the plane is parallel to the base of the cone, in that case, I get a circle. If it's coming in at a nice angle, I can get an ellipse. At a much steeper angle, I get a parabola. If it's going straight down, I can get a hyperbola. I have the cone oriented, of course, north-south. You could have it, of course, oriented east-west, or more painfully, you could have it at a strange angle. And so the question becomes, do you remember how to write down all the equations of conic sections? So if I give you something of the form, ax squared plus bx plus cy squared plus dy plus exy equals f. Depending on what a, b, c, d, e, and f are, can you determine what kind of conic section this is? And there are certain ones you might remember. The circle, this is x minus h squared plus y minus k squared equals r squared. So the center is hk, the radius is r. Right, hopefully we all remember the circle. The next is the ellipse. It's normally x minus h squared over a squared plus y minus b squared. Oh, sorry, not y minus b, y minus k squared over b squared equals 1. And again, one of the great challenges is how do we want to represent things? How do we want to write? There's different notations. How many people have taken a physics class where we've talked about the orbits of the planets and the other cosmic items? Okay. So, Kepler had 3 laws of planetary motion, and he was led to them by studying the orbits of Mars. And Mars was actually one of the best planets to look at. And at one point, he had the orbit of Mars. And again, this is a very challenging problem to do. Essentially, what does Mars orbit about? The sun. It's not actually the sun. The sun is actually one of the foci, and it goes on an ellipse about the sun. But we're doing all the measurements of Mars from the Earth. And so you've got to translate everything. And he had what he thought was the equation of Mars. And he had a nice oval shape. He says, oh, if only this was an ellipse. It actually was an ellipse, but it wasn't the standard form of the ellipse that he knew. So he actually had the equation of the ellipse before he recognized it was an ellipse. And this is one of the challenges in mathematics. Depending on how things are written, it can be very hard to recognize what's going on. This is written a little bit differently than the circle. So let's rewrite the circle in a way that's more symmetric. So I'm going to just divide through by r squared. And now it looks a lot like the ellipse. It looks like just the special case when a and b are the same. Depending on what book you use, sometimes there is a difference between a and sometimes there is a difference between a and b. A lot of books like to use a as the larger of the two. So this would be the equation of an ellipse where the semi-major or the major axis is along the x. If it was along the y, if it was taller than it is fat, then you would switch a and b. And this is just nice notation because there are some relations if you put the foci at minus c and c, and then here is a, I guess minus a, and here is say b. Let me get a little bit lower. Say b minus b. Does anybody remember the geometric definition of an ellipse?
So the distance of points to the foci, the sum of the distance to the foci.
Yes.
Constant.
Excellent. So if I add how far it is from those 2 points, I get something that's constant. Now, when you look at this, there is 1 point where it's or 2 points where it's very easy to calculate the sum of the distances from the foci. And this goes back to one of our general themes: find special cases and grab as much information as you can from them. what point will it be easiest to find the distance to the foci? Which points? Yes. So I think one of them is easier than I think two of them are easier than two of them. Which do you think are easier, the B minus B or the A and minus A? So if it's B minus B, you have to figure out the distance to the two foci.
Oh, A minus.
I think A minus A is much easier. So if we look at the point A comma 0, the distance is, well, this distance here is just A minus C. So the distances are A minus C, and the other one would be A plus C. So the sum of the distances is 2A, right? So now if we know the sum of the distances is 2A, if we go to B, what is the length of that gold line? To get from here to the foci here, it's C to get to the origin, and then A to get all the way down. So if I'm at the point A0, the distance to the foci at C comma 0 is A minus C, and the distance to the foci at negative C comma 0 would be A plus C.
So we're using A plus C minus A minus C?
No. A ellipse is the sum of the two distances is constant. A hyperbola is the difference of the distances is constant. The larger distance minus the smaller distance is constant. So for an ellipse, it's all points, the sum of their distance from the two foci is constant.
So is the distance between the next to A and next to C? Or?
It's the distance from negative C to your point xy plus the distance from C to xy. So any point on the ellipse, here's a point xy, and I calculate how far is xy from the point negative C comma 0, and how far is it from the point C comma 0, and I add the two. And so when I do that, the easiest points to look at are negative A0 and A0, because I can quickly calculate that the sum of the distances is twice A. So if the sum of the distances is twice A, how far would it be from from 0 comma B to negative C comma 0? What would be that length? Do you want to try it? We know the sum of the distances is 2A, right? And so no matter where I am on the ellipse, the distance has to be 2A. So if it has to be 2A, how far is it from this point here to one of the foci? So one way to do this is going to be the square root of B squared plus C squared. But there's another way. We know what this distance is. If the sum of the distances is always 2A, how much must this be? We know these two distances are the same, right? So if the sum of the two golds is 2A, what's one of the golds? A. And this gives, one of the great formulas for conic sections. So we now get A squared is B squared plus C squared. And so so if I know A and B, I can actually find the foci very easily because I know C is going to be the square root of A squared minus B squared. You see that there's actually an asymmetry in the way A and B enter into this equation. And that's why a lot of books like to have A is going to be the semi-major axis, it's going to be the larger one. And B is going to be the semi-minor length, it's going to be the smaller one. Okay, so these are the equations of ellipses. I'm not going to go through the equation of a hyperbola. It's done very similarly. These are all extremely nice. I could be cruel. And as you find out during the semester, that is often the case. What if I happen to give you Did you guys calculate how to do the equations of ellipses that are not aligned with coordinate axes? Normally, this is not done in high school or middle school for good reason. It's bad enough doing regular conic sections. Doing conic sections that are at an angle, dear Lord. How many people have seen how to do this? Okay. If you look at this problem the right way, it's trivial. So let me put in some labels. Here's my x-axis, here's my y-axis. Whenever you take a math class, you should always ask who gives a damn? Why am I taking this class? The answer might be, well, it's required for the major, and if I want the major, I have to take this. But usually it's required for the major for a reason. There's normally a skill set we want you to get from this. One of the big themes of linear algebra is choose a good basis. Find a good basis. For certain problems, some bases are better than others. I brought the Rubik's Cube on the first day of class, where if you hold it at a 30-degree angle, all of a sudden it's essentially the same as a normal 3x3. What I'm saying is this might not be a great basis to use. What might be a better basis to use?
The ones aligned with the axis.
Yeah, the ones that basically just lean back. And if we change our coordinate axes, and we write this as, say the U and the V direction, do we know how to write down the equation in UV space? Yes. It's not that hard to write down the equation in UV space. So what we can do is we can convert the problem to UV space, solve the problem in UV space, and then convert backwards. So this requires you to understand, how do we transform from one basis to another? And so what kind of transformation do you think it's going to be to move from the XY basis to the UV basis? What kind of transformation are we going to need to do?
So that change of base function.
But what kind of transformation is it?
Multiplication.
Well, rotation, right? This is a rotation by theta. So we need to know rotation by theta. Right. Is there anybody here who is a physicist or a physicist in training or physics major? So it is a little bit unfortunate when I teach multivariable calculus at Williams, because I learned spherical coordinates in physics before I learned them in math. And so I have to consciously remind myself not to use the physics notation. The physicists and the mathematicians flip the roles of phi and theta often. And so a lot of times when you're doing transformations, are you rotating the vector or are you rotating the coordinate axis? And depending on which way you do it, you can be off by a minus sign. It doesn't matter as long as you just clearly say, this is what I'm doing. But you've got to be very careful when you're looking at different sources to make sure you do things properly. So if I take the matrix cosine theta, sine theta, sine theta, cosine theta, this is wrong, but just give me 1 second to think how I want to fix this. I'll do it this way. So if I take this matrix, okay, this is called R of theta. It's rotating by theta radians. And if I look at R theta times the vector 1, 0, that's going to just become cosine theta sine theta. And if I do R theta by 0, 1, that's going to become negative sine theta cosine theta. So what this is telling me is, if I start off with the vector 1, 0, I rotate that by theta radians. And if I start off with the vector 0, 1, I'm going to rotate that by theta radians. And so this is a really nice way of just representing what goes on. And so with a little bit of work, what I can do is I can write things down in UV space, solve the equation of the ellipse there, and then come back to XY space. Or conversely, I can start with something in XY space, convert it to something in UV space. I know the equation there, and I can come back. So this suggests that it might actually be easier to write down equations of things like ellipses if I use matrices. Because we already know how to transform from one basis to another using matrices. And we know how to multiply matrices. This is why you really should not be doing ellipses that are not aligned with the coordinate axes until you know linear algebra. Once you know linear algebra, it's very straightforward. I'm rotating by theta radians. So let's look at the standard ellipse. So let's see. Okay, good. So here is the standard ellipse. So this is, let's do x over a squared plus y over b squared equals 1. I can represent this in matrix form as follows. So xy written as a row vector, then the matrix 1 over a squared 0, 0, 1 over b squared, and then xy as a column vector equals 1. So this is basically writing it as v, a, v, I'll do v transpose. So I'll do my vectors as column vectors. If you do your vectors as row vectors, the transpose is in the other place. You have to decide which way you want to do it. I don't really care. But this is a concise way of writing things in terms of matrices. So I basically have the equation v transpose AV equals 1. Well, we know how to write things in UV space. So in UV space, I would have u over a squared plus v over b squared equals 1. And so this would then lead to uv 1 over a squared 0, 0, 1 over b squared uv equals 1. But let's say uv equals r xy. Some rotation applied to xy. I can now substitute, and I would get xy r transpose, and then I'll do my matrix A r xy equals 1. And that's my new matrix. And when you expand that out, you're now going to get an xy term. So I could call this maybe, xy alpha, beta, gamma, delta, xy. So that would be xy alpha x plus beta y, gamma x plus delta y, and then I would get alpha x squared plus beta xy plus dot 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 equals 1. I'm not going to go through all the terms, but now you see we're going to start to get an xy term emerging. So this is a quick review of some of the standard results from linear algebra, and shows how much easier it is to look at these problems if we put them in matrix form. Is I find what is the right basis to study the problem in that basis, and then convert back to the original basis we care about. Okay, any questions about this? What's nice now is you can actually talk about hyperbolas and ellipses in one unified language. And what really changes is this matrix. So for an ellipse, instead of 1 over a squared 0, 0, 1 over b squared, you would have one of the quantities being negative. And you can talk about what are the differences that a negative sign puts in the geometry. Okay. What I want to do now is I want to briefly review eigenvalues, eigenvectors, and talk a little bit about some of their applications. Okay. When I was an undergraduate, I thought eigen was the name of a mathematician. I was impressed at how many different things eigen had studied and how important they all were. So eigen basically means same or characteristic. The idea is, in general, if you have a matrix AV that is equal to some new vector W, and in general W has a different direction and a different magnitude than V. But if W equals lambda V, then W is an eigenvector with eigenvalue lambda. And we normally assume that V is not the zero vector. Because if you do consider the zero vector to be an eigenvector, what is its eigenvalue? Anything. And so again, this goes back to what do we want to define? We talked about the double factorial earlier. The factorial of the factorial just doesn't really show up that much. The factorial is a rapidly growing function. Taking the factorial of the factorial, oh Lord. If you have a standard calculator, when I was a kid, I don't think you could do 80 factorial. I think 80 factorial would be more than enough to just overflow the standard calculator you have. If anybody has a phone or simple device like that, see if you can actually calculate 80 factorial or 100 factorial, even now semi-discretely, or later today, and just see, can the calculator do that? You definitely cannot do the factorial of the factorial. So if we allowed 0 to be a eigenvector, then you would not have a unique eigenvalue for each eigenvector, and that would be annoying. My book freshman year talked about the fact that you could have, as a vector space, a space that has absolutely no elements. Because the way things are stated, for any two elements in the space, well, there are no elements in the space. And so the conditions would be vacuously true for the empty vector space. So for some things, it's useful to have the empty vector space allowed. For other things, it's not. And the book just said, whenever it would cause trouble, we tacitly assume that we are excluding the empty vector space from the theorems below. And you're reading between the lines, we assume, reader, that you are smart enough to realize when we don't want to be studying nothing. But sometimes you look at spaces of functions and the properties you have might be inconsistent. They might not be any non-trivial examples. So it is worth knowing. So the first question, of course, is, why do we care about eigenvectors? So imagine we have a basis of eigenvectors, say V1 through Vn. Then any V can be written as a sum, say k goes from 1 to n of ck vk. So A of V would be the sum k goes from 1 to n of ck a vk. So this is by linearity of the transformation. If you apply a matrix to the sum, that's the same as the sum of the matrix applied to each one. Because the ck's are scalars, I can pull them out. And then you just get the sum k goes from 1 to n of ck lambda k vk. This is the power of eigenvalues and eigenvectors. I can calculate high powers of a matrix very quickly if I have a basis of eigenvectors. Now, I have to, of course, be able to decompose V as a sum of these basis elements. It turns out that that's not that bad to do. It's particularly nice if the vectors have a certain property. Does anybody know what a really good property is for basis to have? What kind of property do you want between the different vectors?
Not linear combinations.
Well, I mean, they can't be linear combinations because they're a basis. So you can't write any one in terms of the other. Do I want to take one of them in the direction of the x-axis and the other one say 1 degree above?
A wide span.
Well, they should all have the same span. What do you want for the angles between them?
Orthonormal.
Orthonormal. You want them to be at right angles. And so if you have a bunch of right angles, it's often very easy to represent things. Essentially, this is exactly what we did a moment ago with the ellipse. When it was not aligned with the coordinate axis, change my basis, lean back. And in that basis, I now have two new directions that are perpendicular to each other. It's often very easy to work. It doesn't have to be. It turns out if A is a real symmetric matrix, A always has an orthonormal basis of eigenvectors. Not every matrix has a basis of eigenvectors. With probability 1, any matrix you choose at random from the world will be diagonalizable, and it will have a basis of eigenvectors, and you can do these calculations very quickly. Why is this particularly nice? Well, let's say I want to calculate A to the n of V. Dot, 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 dot. That would just be the sum k goes from 1 to n of ck lambda k to the n vk. And now you really see the power of having a basis of eigenvectors. If I want to calculate a high power of a matrix A acting on a vector, I can do this by just applying the matrix to each basis vector. And all that does is it rescales each basis vector by the eigenvalue. So if I do this n times, I'm just raising the elements to the n power. This is much better computationally than calculating high powers of a matrix. If we wanted to calculate high powers of a matrix, this is matrix multiplication. You can actually do this using things like Strasson's algorithm, as well as what we did before, the fast multiplication. So it'd be wonderful if n is a perfect power of 2. If not, we play that game we did before. Okay. So in terms of applications, one of my favorites is the Fibonacci numbers. And there's lots of ways to define them. I've done a lot of research with students on this. I am proud to be the president-elect of the Fibonacci Association. And the rule is the n plus first is the nth plus the n minus 1. So what we're going to do is we're going to define, let's say Vn to be Fn minus 1. So Vn plus 1 is going to be Fn plus 1 Fn. But what's Fn plus 1? That's just going to be Fn plus Fn minus 1. And then Fn plus 0, Fn minus 1 is the bottom. So this is the same as 1110 times Fn minus 1. So Vn plus 1 is 1110 Vn. And we can let A be the matrix 1110. Has anybody ever read the directions on shampoo? Okay, good. What are the directions on shampoo? What are you supposed to do? Lather, rinse, and then there's one other word. Nope. Lather, rinse, repeat. So you keep doing this. We know Vn plus 1 is this matrix A times Vn. Now that we have this, let's do it again. So Vn plus 1 is AVn, or it's A squared Vn minus 1, or A cubed Vn minus 2, dot, dot, dot. And then the question is, how far do we go? Well, we start off with A to the first power V sub n. The power of A and the subscript of V add up to n plus 1. The next one is A squared Vn minus 1. It still adds up to n plus 1. So if I want to go all the way down to V1, what power of A should I have? So what power of A do I need? So in the first one, I had A to the first power V sub n. 1 plus n is n plus 1. The second one, I had a squared Vn minus 1. The power of a went up by 1. The index went down by 1. The sum is still n plus 1. So for the final one, so if I did n minus 1, I would get n minus 1 plus 1 is n. Right? The sum of the index and the sum of the power of a in the subscript is always n plus 1. So it should just be n. So this is a great way to make sure you don't make a mistake when you're doing things, is just notice the pattern as you're going down. So if I want to calculate the n plus first Fibonacci number, or the nth Fibonacci number, I just have to calculate the nth power of a. So what I need to do is find the eigenvalues and eigenvectors of a. So find eigenvalues, eigenvectors of a. The main way we do this is we look at the determinant of a minus lambda I equals 0. And the reason is if AV equals lambda V, then you get a minus lambda I acting on V equals 0. This is where the determinant equation comes from. If AV equals lambda V, well, lambda V is just lambda times the identity matrix acting on V. And now when I subtract, I have this new matrix that acts on V and it sends V to 0. So the question is, what element of V is in the null space of the operator a minus lambda I? So what's sent to 0? Well, this is going to give me a polynomial of degree 2 in lambda to solve. Can we solve polynomials of degree 2? Yeah. What would we use? Quadratic equation. So you can now go through this, and this would become the determinant of a minus lambda I. So it would be 1 minus lambda, 1, 1, negative lambda equals 0, or 1 minus lambda times negative lambda minus 1 equals 0. And then you could find what is lambda. Once you have lambda, then you can solve and find V. So I will leave this as an exercise for you to do. I strongly urge you, especially if it's been a while since you've done linear algebra, or if you're a little bit shaky on your linear algebra, find lambda, find the eigenvalues. Once you have the eigenvalues, find the eigenvectors. Once you have the eigenvectors, then write the initial condition, V1 in terms of the eigenvectors, and then write down a general formula for the nth Fibonacci number. And this is how you'll get Binet's formula. It's a beautiful way to get there from some basic linear algebra. In practice, Lord help us if we have to solve the determinant of a minus lambda I if A is a 10,000 by 10,000 matrix. It is criminal to leave you with the impression that this is something we can do. You would have to be very concerned about numerical stability. If I have a huge matrix like this with just real numbers as entries, how confident am I that I'm going to be able to do all these operations and in the end actually have a solution? And again, you're trying to really emphasize the difference between pure math and applied math. Theoretically, here's my equations. I have n roots, find the corresponding vectors, write things down. On the applied side, how do we actually do this? And so a lot of the algorithms we have are not necessarily going to be easy ones to work with. All right, so again, I want to spend some time at the beginning of the semester reviewing linear algebra. If this is the right pace for you, please let me know. If it's too fast or too slow, let me know so I can try to gouge the class accordingly. Years ago, I was teaching differential equations. I'll tell that story later because it's 9:50. All right, so I will stop here, and then we will continue on the next class, which I think is Friday.